13.8 billion years ago from a very hot and dense singularity filled with fundamental particles and radiations to the largest expansion, or actually the Big Bang. The universe started expanding rapidly and cooled down, leading to the formation of the elementary particles, which we classify them now under the Standard Model of Particles. The Standard Model of Particles is a theoretical framework describing the fundamental particles and the forces in the universe, excluding gravity. The Standard Model of Particles is divided into two categories: fermions, which make up matter including three generations, each of two quarks and two leptons. The first generation constitutes the atom. As you can see, an atom is made up of a nucleus surrounded by an electronic cloud. It is the space of how likely you can find an electron. And this electron is an elementary particle. However, protons and neutrons, which constitute the nucleus, aren't considered as elementary particles, but rather as subatomic particles. Since till now, we know they are made up of three quarks. For example, a proton is made up of two up quarks and one down quark. The second category includes bosons, which are force carrier particles. We have gauge bosons having a spin of 1, such as photons carrying the electromagnetic force, gluons carrying the strong nuclear force, W+- and Z bosons carry the weak nuclear force. We also have a scalar boson, which is the Higgs boson, that we'll be discussing now. And here's the question: why do most of these elementary particles have masses? And why do some, such as photons, remain massless? In 1964, the question led the British theoretical physicist Peter Higgs to propose the existence of the Higgs field as an excitation field occupying the space, so that when a particle interacts with it, it acquires a certain mass. However, his proposition remained as a hypothesis until it was verified at CERN, the world's largest particle accelerator under the ground of the France-Switzerland borders. On July 2012, the Higgs boson's decays were detected and Peter Higgs won the 2013 Nobel Prize. Here is how CERN works. Protons are accelerated to the 99.99 the speed of light, creating high-energy collisions detected by the detectors. According to the energy-mass equivalence, the energy from high collisions can produce new particles including the Higgs boson. Only the effects of the Higgs bosons were detected because the boson is unstable and decays immediately in just 10 exponent minus 22 seconds. Here is a graph by Atlas showing the mass of a Higgs boson of approximately 125 giga-electron-volts. For better representation, here is a Feynman diagram for one of these experiments done. Two incoming gluons. They exchange a virtual top quark which producing top-anti-top pair. This pair annihilates, forming a real Higgs boson decaying into two Z bosons, in which one is virtual. This is concerning the Higgs discovery, and now let's talk about the Higgs mechanism. According to quantum field theory, each of the elementary particles has a field occupying the space, as well as for the Higgs field. The vacuum isn't empty, rather filled with quantum fluctuations. When a particle interacts with the Higgs field, it acquires mass which is proportional to the strength of interaction. For example, the top quark interacts strongly with the Higgs field, making it the most massive quark of mass approximately 172.76 giga-electron-volts per speed of light squared. On the other hand, photons don't interact with the Higgs field, and thus they are massless particles and travel at the speed of light. So without the Higgs field, all particles will have the ability to travel at the speed of light. Yet, there is a problem concerning the weak nuclear force bosons. According to the Lagrangian equation, all of the gauge bosons must be massless. However, the W and Z bosons carry a large mass. Here is the physicist Sheldon Glashow, who solved this mystery by unifying the electromagnetism with the weak force in an electroweak interaction. It states that Higgs field has a non-zero vacuum expectation value, VEV, meaning it has a constant value everywhere, even in the vacuum. In the early universe, at high energies, the electroweak force is symmetric. The Lagrangian describing the system is invariant under certain transformations. As the universe cooled, it underwent spontaneous symmetry breaking. The Higgs field acquired a VeV, breaking this symmetry and giving mass to W and Z bosons while keeping the photon massless. The Higgs field is described by a potential that has a Mexican hat shape. At the top of the hat, the symmetry is maintained, but as the field settles into a minimum or the rim, it acquires a VeV which is not equal to 0 but rather equal to 246 gigaelectron volts, and thus the symmetry is broken.